Okay, this is problem number 69 from chapter 24, electric field. So question is about a thin wire with linear charge density, that's a charge per unit length, that's linear charge density lambda, which is lambda naught y naught times 1 over 4 plus 1 over y, where y naught ranges from 1 meter to infinity. So when lambda naught is 1.45 times 10 power minus 5 coulomb per meter, so we have to find the magnitude of electric field due to this wire at the origin. So y is measured in meters. Okay, so we can uh, we can express the configuration of the linear charge density, or the small charge element, the small element of field of the thin wire as this. So suppose this is a small region where represents dy and which contains the number of charge dq, so that the charge density can be expressed as dq over dy. So that is nothing but just dq, small charge element, equals to lambda times dy, where lambda is given. So dq can be further expressed as lambda times dy. So within this region, let's consider the field has the value of dE, so that these small segments of dE, when integrated, will give us the total field E, so that E equals to integration of dE, where the limits of integration ranges from y naught to infinity, which is given in question. So as we know, electric field E equals to the integration of k dq over r squared, the distance. If we express in vector form, this will r is a unit vector along the direction of E. So here r square is the distance of is the length of this thin wire, which is y, and the distance square means the y square. Okay, further this is k, but we have dq is lambda times dy, and lambda is this is lambda. Okay, this term is lambda, and this is dy. All together gives you dq, and r square is just y square, and this is the direction of the field, because you have to calculate the field of this magnitude of electric field due to this wire at the origin. So it's directed toward the negative axis. Consider the y-axis, let's say that's why j. So you can pull out the constant out, like k, lambda naught, y naught, and j. The integration constant, I mean the terms that doesn't depend on y, can be pulled out. Okay, so the term inside the integration will be this, and you can integrate this term. So it will be just, you can write y square as a y power minus 2, and integration of this will be y power minus 2 plus 1 over minus 2 plus 1, this. And similarly for this, the range of the y is from y naught to infinity. So you can write that, and further you can further solve that, and you can use the value of integration, the limit of integration here. So 1 over infinity will be like 0. That's why you will get the value that corresponds to the lower limit only. So you can use as y naught ranges from 1 to infinity, so you can use its lower limit 1 meter. So we have the value of constant k, and lambda naught is also given. So whenever you use all the values, this is k, this is lambda naught, and this is z. So y 1 over 4 y naught means 4 times 1, 2 times 1 is square. It's nothing like same. So that's why whenever you solve all the mathematics, you'll get this value. This is the required value for electric field at origin, and this is in vector form. You can write this as a magnitude. So this is how you can solve this kind of problem. This is one of the tricky problems that I'd say from this chapter. However, it's not that tough. You'll get this how the given values and the configuration can be used. Okay, thank you.